Hello, and welcome to this presentation, Getting Started with the FSW, Statistics Measurements. In this presentation, we'll explain how to perform statistical analysis of signals using a Rohde Schwarz FSW series signal and spectrum analyzer. CCDF, or the complementary cumulative distribution function, is one of the statistical measurements supported by the FSW. We'll provide a brief overview of CCDF in just a few moments, but please see the separate presentation, Understanding CCDF, if you'd like a more in-depth introduction to this topic. Statistics measurements are standard spectrum measurements on the FSW and are supported on all FSW series analyzers. Statistics measurements are used to measure the amplitude or power distribution of radio frequency signals. This is of particular interest when looking at signals whose amplitudes vary or change over time. These types of variable amplitude signals are in fact quite common in modern wireless communications and in other applications. Statistical information is often used to quantify this variation in the form of peak-to-average power ratio, also commonly called crest factor, and in turn this information is used when designing systems and selecting components. Two different types of statistics measurements are supported on the FSW. The first is the amplitude probability distribution, or APD, and the second is the complementary cumulative distribution function, or CCDF. We'll provide a short explanation of each of these on the next couple of slides. The input signal is measured in zero-span mode, and statistics are collected over a user-defined analysis bandwidth. The results are typically represented both graphically and numerically. Furthermore, a gated trigger can be used to make these measurements only over a given time range, and this can be useful when making statistics measurements of pulsed or bursted signals. Let's pause briefly to explain APD and CCDF. APD is the amplitude probability distribution and shows the probability that a signal takes on a given amplitude value. The amplitude values of the signal are measured and assigned to amplitude ranges, or bins, and these are then plotted or displayed in the form of a histogram. Each bar in this histogram then represents the percentage of measured values, which fall within each bin. The x-axis shows the amplitude as absolute values in units of dBm, and the y-axis indicates the percentage of total measured values represented by each bin. CCDF, on the other hand, shows the cumulative probability, in percent, that signal power exceeds the mean value. On a CCDF graph, the x-axis shows relative amplitude above mean signal power. The origin of this graph, therefore, represents the mean or average power level, that is 0 dB. The cumulative probability of exceeding the mean by n dB or more is then plotted. For example, this point along the graph indicates that 10% of the time, the measured signal was 11 dB or more above the mean signal power. Therefore, the more a CCDF curve moves to the right, the more often the signal takes on values that are significantly above the mean value, and thus the higher crest factor or peak-to-average power ratio of the signal. To start statistics measurements on the FSW, press the Measure Hard key and then select APD or CCDF from the list of statistics measurements. These are standard spectrum measurements and do not require any additional hardware, software, or license code. Here we see the APD measurement main screen. Configuration settings are accessed via the buttons on the right. The default view shows both graphical results as well as numerical results beneath them. The CCDF measurement screen is laid out similarly to the APD screen, with configuration buttons on the right, graphical results at the top, and numerical results along the bottom. In the remainder of this presentation, we'll go step by step through both APD and CCDF measurements and explain how to configure measurement parameters and interpret results. Configuring APD measurements is done by pressing APD config. The most important parameter is the analysis bandwidth, which must be as large or slightly larger than the bandwidth of the signal being measured. We'll talk about this in more detail in just a few moments. The other important parameter is the number of samples, which is the number of power measurements that are used in calculating statistics. Recall that statistics measurements are made in zero-span mode, and the sweep time is calculated from the user-defined number of samples. As mentioned earlier, the FSW also supports gated statistics measurements, and these will be described in detail towards the end of this presentation. The final configuration item is Adjust Settings, which automatically adjusts the reference level and range based on the input signal. Pressing Adjust Settings is recommended for obtaining optimal measurement accuracy. CCDF configuration is essentially the same as APD configuration, but with two additional parameters. The first is the percent marker, which can be placed on any arbitrary point on the CCDF trace in order to read off the cumulative probability. This marker can be used to obtain values beyond the default fixed percentage values provided on the CCDF results. The other parameter is normal distribution. This can be used to enable or disable a normal distribution trace, shown in red, on the CCDF result display. Let's return to the topic of analysis bandwidth. It's very important that the analysis bandwidth be configured wide enough to measure the complete signal, including any peaks. In this example, the maximum signal width is 40 MHz, and setting analysis bandwidth to 40 MHz ensures that all of the signal is being correctly measured. On the other hand, if the analysis bandwidth is set too low, the measured statistical values will be incorrect. The picture on the right shows the same signal, but with an analysis bandwidth set to only 10 MHz. As we can see from these traces, too narrow of an analysis bandwidth will cause peak powers to be truncated, and thus the CCDF values and the crest factor will also be incorrectly low. Failing to set the analysis bandwidth properly is the most common issue encountered when making statistical measurements. Now let's look at a properly configured APD measurement result. Recall that the x-axis represents absolute measured power levels in dBm, and the y-axis is the number of samples in each bin. The value in the top left corner of the screen shows the histogram resolution, that is, the width of a single bar or bin in the results. In this example, each vertical line corresponds to a bin width or amplitude range of 0.1 dB. The numeric results along the bottom of the screen include the mean and peak power values, as well as the crest factor or peak-to-average power ratio, which is simply the peak value minus the mean value. Here is a CCDF measurement result. The yellow trace shows the cumulative probabilities calculated from the measured values. The optional red trace is a purely Gaussian curve. Recall that the x-axis shows relative powers in dB above the mean power, and thus the left end of the x-axis corresponds to the mean power or 0 dB. The numeric results along the bottom give the mean and peak powers as absolute values in dBm, and the crest factor or peak-to-average power ratio in dB. As before, note that this number is simply peak minus mean. Spot values for points on the CCDF curve, such as 10%, 1%, etc., are automatically given, but the percent marker can be used to determine values at any arbitrary point along the curve. Although only one statistical measurement, APD or CCDF, can be actively running at a time, it is possible to configure and have both measurements open in separate tabs, as shown here. Switching between these measurement tabs manually is done by clicking on a tab to make it the active measurement. However, the FSW's sequencer function can be used to automatically switch back and forth between these measurements. Please see the FSW documentation if you'd like more information about how to configure and use the sequencer function. Our final topic is gating. Gate ranges are used to define a time domain interval over which measurements are made. This is particularly useful when performing statistical measurements on the active part of a pulsed or bursted signal. The user must provide the signal period, and within each period, up to 3 gate ranges can be defined. An external trigger, or a power trigger, that is a trigger based on measured signal power, can be used along with an optional trigger offset time to define the gate range reference time T0. Gate range start and stop times are then defined relative to this reference point. Gate triggers and their ranges are configured using Edit Gate Ranges in both the APD and CCDF configuration dialogs. Up to 3 gates can be defined for each of the FSW's 6 available spectrum traces. Note, however, that the period must be the same for all traces. Gate range start and stop times are all defined relative to the reference time t = 0. It's also important to ensure that the period is not longer than the total measurement time, which in turn depends on the configured bandwidth and the sample count. This is easy to verify since the measurement time is displayed at the top of the main screen. Here, the total measurement time is 101.6 milliseconds. Let's end with a brief summary. Statistical analysis is a standard spectrum measurement feature on all Rohde Schwarz FSW series signal and spectrum analyzers. The FSW supports both the amplitude probability distribution function, APD, and the complementary cumulative distribution function, CCDF. These measurements provide information about the distribution of signal power, as well as the burstiness of the signal, that is the crest factor or peak-to-average power ratio. Configuring these measurements is very straightforward. The user simply provides the analysis bandwidth and sample count, and the results are displayed both graphically and as numeric values. And finally, gate ranges can be used to make statistical measurements only over a portion of a periodic signal. This concludes our presentation, Getting Started with the FSW Statistics Measurements. If you'd like to learn more about statistical measurements, other spectrum measurements, or spectrum analyzers from Rohde & Schwarz, please see the links in the video description. Thanks for watching.